total will be 31.9 gallons per minute. So we have a makeup water of 179.4 gallons per minute. So the makeup water, we need 179.4 gallons per minute to replenish the water losses inside the cooling tower. Another parameter that is needed to look into in operating a cooling tower is the static air horsepower, or SAHP. So in evaluating a cooling tower, owning and operating cost, fan horsepower requirements can be a significant factor. Why? Why do we need to concentrate? Why do we need to take into consideration the fan horsepower? Because the fan in a cooling tower constitutes a relatively big portion on the cost of the cooling tower and its operation and its construction. So large air quantities are circulated through cooling towers at exit velocities about 10.2 meters per second, maximum for induced draft towers. So fans are needed to circulate the air in induced draft towers. So to compute for the static air horsepower, we have this equation where Q is air volume in feet cube per minute. Then HS is the static head, inches of water. Then density of the water at ambient temperature in pounds per feet cube. So we'll use this equation to determine how much horsepower is needed to operate the fan in a cooling tower. So theoretically, operating at half speed will reduce airflow by 50% while decreasing horsepower in 1/8 of a full speed operation. So in a cooling tower system, we can operate the fans at half of its speed, and by doing that, we can reduce the horsepower requirement into 1/8 of the full speed operation. However, in reality, half-speed operation will require about 17% of the horsepower at full speed. So it is not really 1/8, but we will consider the 17% of the horsepower at full speed as a result of inherent motor losses at lighter loads. So this is figure 12.17, typical plot of cooling tower performance at varying fan speeds. So we have an example here. So for a 60-degree Fahrenheit wet bulb temperature, which is around here, 60 degrees Fahrenheit, then a 20-degree Fahrenheit range, a living water temperature is slightly below 85 degrees Fahrenheit. So our wet bulb temperature is 60 degrees Fahrenheit, and the cold water temperature is around 85. So we're going to operate it at half speed. If we have a 100 horsepower motor, we'll only consume 17 horsepower to operate the fan. So 83 horsepower would be saved when operating it at half speed. So there's a very large power saved when we are operating the fans at half speed. It's a matter of weighing which is more costly, using two fans or operating a fan at full speed. So the last parameter in considering in operating a cooling tower is the pumping horsepower. Like the fans, pumps constitutes a very large amount in the cooling tower costings. Then the pumping horsepower is computed as the flow rate of water in gallons per minute times the total static head in feet over 3960 times the pump efficiency. Then Alan will discuss about the ChE method and the use of nomograph.
Good classmates, we're about to discuss the ChE method and the use of nomograph method. Well, this method is used according to the inlet and the outlet electrons. The physical location of the connectors is important because we may connect the strings in any of the position. So this is the input and the output. The feed is the input, is the warm water feed. The vapor is the output, it is the also the operation is then as discussed earlier, the liquor loss and root loss. Then the liquor is also output, is the cooled water output. So shot-to-shot method is used for the determination of the power characteristic KAV over L by numerical integration. This technique of numerical integration was named after looping ChE, a national mathematician known as a founding mother of Russian mathematics. So this is the formula for numerical integration using ChE. KAV over L is equal to the integral of dt over HW minus HA from T2 to T1, which is by Chebyshev method, is equal to T1 minus T2 over 4 times 1 over delta H1 plus 1 over delta H2 plus 1 over delta H3 plus 1 over delta H4. HW is the enthalpy of air-water vapor mixture about water temperature, where HA is the enthalpy of air-water vapor mixture at about temperature, also in degree per pound. So this is the formula for getting delta H1, delta H2, delta H3, and typographical error, that should be delta H4. So in order to make it better, a sample problem will be presented. This problem is taken from the Paris Chemical Engineers Handbook 7th edition. Determine the theoretically required KAV over L value for a cooling liquid from 105 degrees Fahrenheit inlet water, 85 degrees Fahrenheit outlet water, 78 degrees Fahrenheit ambient wet bulb temperature, and an L over D ratio of 0.77. So we will use here, what we use here is the ChE method. We can have the H1 from the air-water vapor mixture. It is equal to 41.58 BTU per pound.
She's got you high and you don't even know yet. She's got you high and you don't even know yet. The sun's in the sky, it's warming up your bare legs and you can't deny